Hello! Kamusta kayong lahat? Tom at Jenny nga pala ang inyong tropang estudyante. Ngayon, kasama natin ng ating professor upang turuan tayo tungkol sa limits and graphs. So, umpisan na natin, Professor.
Limits and graphs. Suppose that a function f has the graph shown on the right. Our goal is to describe the behavior of f in the vicinity of x equal to 1 in a concise manner. Let's first notice that the value f of 1 is equal to 1. Yet if x is close but not equal to 1, then f of x is close to 2. In fact, the closer x is to 1, the closer f of x is to 2. So the number 2 is crucial in describing the behavior of f near 1. The way that we describe this behavior is to say that 2 is the limit of f of x as x approaches 1. This is written compactly in the manner shown. To be a little more precise, the reason 2 is the limit as x approaches 1 is that for any interval centered at 2 on the y-axis, no matter how small, the number f of x will be in that interval for all x other than 1 in some sufficiently small interval centered at 1 on the x-axis. Also, we point out that the limit as x approaches 1 has nothing to do with the value of f at 1. We could change f of 1 to any number we like, or even leave it undefined, and the limit remains 2. Note that if the limit as x approaches 1 is different from f of 1, there's a hole in the graph at the point 1, 2. If f of 1 were equal to the limit, the hole would be filled. In fact, at any point where the graph of f is continuous, the y-coordinate, that is, the value of f, will equal the limit of f as x approaches the x-coordinate of that point. So value and limit coincide wherever the graph of f is continuous. This idea is the basis of the mathematical definition of continuity that you will see later. Let's look at another example. Again, suppose that f is the function whose graph is shown on the right. Here the interesting behavior of the function is in the vicinity of x equals 0. Let's first notice that the value f of 0 is equal to 2. If x is close to and less than 0, then f of x is close to 2. In fact, the closer x is to 0, while x is less than 0, the closer f of x is to 2. But if x is close to and greater than 0, then f of x is close to 1. In fact, the closer x is to 0, while being greater than 0, the closer f of x is to 1. Therefore, there is no number that can serve as the limit of f of x as x approaches 0. That is, the limit does not exist. However, we can describe the behavior of f near x equals 0 in terms of one-sided limits. Here, 2 is the limit of f of x as x approaches 0 from the left or from below. This means that for any interval centered at 2 on the y-axis, f of x will be in that interval whenever x is in a sufficiently small interval whose right endpoint is 0. 1 is the limit of f of x as x approaches 0 from the right or from above. This means that for any interval centered at 1 on the y-axis, f of x will be in that interval whenever x is in a sufficiently small open interval whose left endpoint is 0. This example illustrates a very important fact about limits. The limit of f of x as x approaches some number a exists if and only if both of the one-sided limits as x approaches a exist and coincide. That is, if and only if f of x approaches the same number as x approaches a from both the left and the right. When this happens, the limit equals the common value of the one-sided limits. Another example. Again, suppose that f is the function whose graph is shown on the right. Here the interesting behavior of f is in the vicinity of x equal to 2. Notice that f of 2 is undefined, and the line x equals 2 is a vertical asymptote. If x is close to 2 while less than 2, then f of x is large and positive. In fact, the closer x is to 2 while less than 2, the larger f of x is. If x is close to 2 while greater than 2, then f of x is large and negative. Therefore, there is no number that can serve as the limit of f of x as x approaches 2. That is, the limit does not exist. In fact, neither of the one-sided limits as x approaches 2 exists. However, we can describe the behavior of the function near the vertical asymptote in terms of infinite one-sided limits. Here we say that the limit of f of x as x approaches 2 from the left is plus infinity, and we say that the limit as x approaches 2 from the right is negative infinity. The limit from the left is positive infinity because given any positive number, no matter how large, f of x will be greater than that number for all x in a sufficiently small open interval whose right endpoint is 2. The limit from the right is negative infinity because given any negative number, no matter how large, f of x will be less than that number for all x in a sufficiently small open interval whose left endpoint is 2. We should point out that in this example, since the one-sided limits do not agree, the limit as x approaches 2 does not exist even in an infinite sense. Now let's look at a few example exercises. This is the first one. Given the function graphed here, we want to determine a, the value f of 1, b, the limit of f of x as x approaches 1 from the left, c, the limit of f of x as x approaches 1 from the right, and d, the two-sided limit of f of x as x approaches 1. Because the point 1, 1 is on the graph, we conclude that f of 1 is equal to 1. As x approaches 2 from the left, the corresponding y-coordinates, or function values, are approaching 2, so the left-sided limit is 2. As x approaches 1 from the right, the corresponding function values are approaching 0, so the right-sided limit as x approaches 1 equals 0. Now, since the two one-sided limits do not agree, the limit as x approaches 1 of f of x does not exist. This example is similar to the previous one. Given the function graphed here, we'd like to determine a, the value of the function at 2, b, the limit as x approaches 2 from the left, c, the limit as x approaches 2 from the right, and d, the limit as x approaches 2. f of 2 is equal to 0 because the point 2, 0 is on the graph. As x approaches 2 from the left, the corresponding y-coordinates, or function values, are approaching 0, so the limit as x approaches 2 from the left equals 0. As x approaches 2 from the right, function values are negative and getting larger and larger, so the limit as x approaches 2 from the right is negative infinity. Now, because the two one-sided limits do not agree, or simply because the right-sided limit does not exist, the limit as x approaches 2 of f of x does not exist. In this example exercise, we want to sketch the graph of a function f, defined for x greater than -1 and less than 3, so that the list of conditions concerning limits and or values at x equal to -1, 0, 1, 2, and 3 are true. Let's begin at the left endpoint and work our way from left to right. f of -1 is undefined, and the right-sided limit as x approaches -1 is 2. So near -1, the graph might look something like this. Since f of 0 is 1, we'll plot the point 0, 1, and since the limit as x approaches 0 is 0, the graph might look something like this between -1 and 0. Next, we plot a point at 1, 0, and we note that the infinite left-sided limit at 1 means that the line x equals 1 is a vertical asymptote. Since f of x approaches positive infinity as x approaches 1 from the left, and again using the fact that the limit at 0 is 0, we conclude that the graph might look something like this between 0 and 1. Next, let's use the fact that the limit as x approaches 1 from the right is 1 to continue the graph past 1. The value at 2 and the left-sided limit as x approaches 2 are both 2, and so we plot the point 2, 2, and then sketch the graph for x between 1 and 2, something like this. Now, since the right-sided limit as x approaches 2 is 0, we continue the graph past 2 like this. And finally, we finish the graph, making use of the fact that the limit as x approaches 3 from the left is equal to 1. There are many other ways that this graph might have been drawn. Other possibilities need only show the correct values and limiting behavior at x equals -1, 0, 1, 2, and 3. In particular, this is another possibility where the graph wiggles around a bit more between those values of x.